students. Continuing our lectures on alloys or solid solution. So, in our lecture number 33, you will find that I have discussed about solid solution. So, this lecture can be considered a continuation of that lecture. Now, we will address the problem in a different way. Today, we will start with something called a superalloy. Now, the superalloy was maybe introduced or came into existence in World War II, where aircraft turbine engines required high performance at elevated temperature. So there were some superchargers. So the aircraft turbine engines and the rocket, they required high performance at high temperature. Temperature was high, therefore the need required for some alloys with some very unique properties were searched for. And also, apart from this high temperature performance, these superalloys were also required to give good low temperature ductility. As well as surface stability. So we can see that we are actually asking for a lot. We are asking for high performance at both low and high temperature as well as surface stability. So that is why the name super is given to these sort of alloys. Now the superalloys are based upon, they are based on a group 8B elements. And there's various combination of the transition metals like iron, cobalt, nickel, chromium, and to some extent these are the elements which are mainly used. These are the major contribution comes from these elements, and to some lesser extent elements like tungsten, molybdenum, tantalum, niobium, titanium and aluminum are also used in making a superalloy. Now there are three major classes of superalloy. So there are three major classes of superalloy. One is nickel based superalloy, Second one is iron-based superalloy, and the third one is cobalt-based superalloy. So these are the three major classes of superalloy. And the major phases involved in the nickel phase superalloy are gamma and gamma prime, where gamma is basically a continuous matrix so the construction or the gamma phase is actually a continuous matrix. In which FCC nickel based austenitic phase is present, and it contains to some extent cobalt, chromium, molybdenum and tungsten. This forms the gamma phase, and the gamma prime it consists of Ni3, aluminum and titanium. This is a typical gamma prime nickel-based superalloy. So it is the properties are there is a precipitating phase, and this precipitating phase is in compatibility with the continuous phase, and there is a close match between the lattice parameter and the matrix, and so this pivot phase is in the matrix, and there is a lattice parameter match. Between the precipitate and the matrix. Gamma prime are basically preferred over gamma because gamma prime have the properties like it is chemically compatible. Then it gives a homogeneous precipitation. And lastly, it has a long time stability. Now, coming to its performance at temperature, it has been observed that if we increase the temperature, then the flow stress of gamma prime, it also increases. Now, alloys, as we have already given the introduction of alloys, there is something called a superlattice in alloys, a superlattice formation. What is a superlattice formation? Now, if suppose there are A and P atoms in an alloy, and the A atoms are supposed to be at the alpha sites, and the B atoms are supposed to be at the beta sites. So both A and B atoms are at the respective alpha and beta sites. We will say that the atoms are right atoms. However, if some of the alpha sites are occupied by B atoms and vice versa, then we say that those atoms are wrong atoms. So if all the atoms are right atoms, we call it a superlattice, which is a hypothetical or very rare concept. You need to be defect free, the material needs to be defect free. Okay, now based upon these right and wrong atoms, we define a parameter. It's called an order parameter. And it is alpha, and it is equal to R minus W by N, right minus wrong atoms, and N is actually R plus W, the total number of atoms. So this can be also be expressed as 2R minus N by N. Now, if R is equal to N, that means all the atoms are right atoms, and so this is not alpha, actually this is L. Consider it as L. So if all the atoms are right atoms, then you will get L is equal to 1. So it implies that there is a complete order. Another way by which a complete order can be attained, interestingly, is when all the atoms are wrong atoms. Then also we get L is equal to 1, and it is also implying a complete order. That means in this case, all the A atoms are at the beta sites, and all the B atoms are at the alpha sites. So even then the complete order is obtained. Now, the only condition where there is complete disorder is when half of the atoms are right and half of them are wrong. So when R is equal to N by 2. So this is the only case when the value of L, which is 2R minus N by N, this is equal to 0, and it implies complete disorder. Now, for physical interest, the value of L is between 0 and 1. Now, coming to the energetics part, now we can understand that since at absolute zero, at 0 Kelvin, at this stage, the alloy should be completely ordered. That means L should be equal to 1. And in this condition, if someone wants to produce a disorder in the system, then energy must be required to produce a disorder. So at this case, energy to be supplied to cause disorder. Now in this case, if we interchange the right and the wrong atoms, that means we take the right atoms to the wrong side and the wrong atom to the right side, then the change in wrong atom is equal to minus change in the right atom, and it should be equal to 2. Now, in thermal equilibrium, the change in free energy, to delta F as the change in free energy, and we assume that this free energy change is associated with the change in number of wrong atoms. And so this delta F, this should be equal to 0. It should vanish if we are talking about thermal equilibrium. So delta W should be much less than the total number of wrong atoms. Now, again, for the sake of mathematics, if we consider that phi RW, if this is the energy required to produce a pair of wrong atoms, then we can write the expression for something called configurational entropy. The word entropy is important because we are changing the order of the system. We are changing by introducing wrong atoms. We have disturbed the order. We have increased the order. We increase the disorder of the system. So our configurational entropy is written as SCF. It is equal to Coulomb constant into n log n, the total number of atoms, minus R log R minus W log W. Now, as I have said, if all the atoms are right, if all atoms are either right or wrong, it means if n is equal to R or n is equal to W, then there is a complete order, and this complete order is called the superladder state. Now, in this superladder state, if we somehow increase the temperature increase in the superladder state will introduce some defects. That means there will be some interchange of the right. There will be some deviations. Total number of atoms will not be either right or wrong. There will be some changes. And so we can find that at lower temperature the crystals are more ordered. Now, various types of atoms in a solid solution distribution random. For example, if we take the example of, say, copper zinc, they are containing brass. Brass is basically an alloy of copper and zinc. If you look at the structure, the center point is copper, whereas there are 8 corners where zinc is located. This is zinc. Now, another way of representation of this copper brass system is if zinc is placed at the center and the copper atoms are at the corners. So basically, there are two interpenetrating cubic lattices. See that there are two interpenetrating simple cubic lattices are there, one made up of copper at the center and zinc at the corners, and the other made up of zinc at the center and copper at the corners. Now, in this case again, as we are increasing the temperature, so increasing the temperature in this case is reducing the order. Now, at certain temperature Tc, the order is found to drop rapidly. So there will be certain temperature up to which the order will be maintained. But if you when you cross that threshold temperature Tc, the order will drop very rapidly. And so these sort of structures are also found in other materials. For example, if we take an alloy of gold and copper, that means AuCu3, or platinum Cu3, or FeNi3. All these orders will show a similar structure with retain lattice. Now, another property of an ordered state is that the XRD, you get some extra XRD lines. An ordered state is also characterized by extra diffraction lines. However, with temperature increase, they disappear, which is quite natural because the order has been hampered. And these extra lines are planes of atoms and may have a different seed power. So these extra lines are due to some planes of atoms. In different seat powers. So, and apart from this extra ordered lines, and signature of an ordered alloy is also the extra specific heat. This is a signature of the ordered state. So the extra specific heat is, if you plot specific heat or C, having unit calorie per gram degree centigrade with temperature. So it will show a plot. Show peak, and then it will slowly gradually come down. Now this temperature is the Tc, or the critical temperature, after which, so initially the specific heat rises, and after the critical temperature the specific heat falls down. That means that disorder has been introduced into the system, or there is a rapid fall in the order in the system. Now this rise in temperature is, as since we have already explained, that when a lattice is in a completely ordered state, so you require some energy to break its order. So that energy is this much of energy, but once that has been achieved at a certain temperature, then after that, it actually no more further energy is required to create an order because the threshold energy has been crossed. Now with increasing temperature, the order actually reduces. Another practical applications of a superlattice or super alloy is the electrical conductivity. The electrical conductivity or the electrical conductivity increases or the electrical resistivity decreases, whatever we call it. So sigma increases or rho decreases. Now this decrease in resistivity can be explained by electron becoming more perfect. So the periodicity of the atoms is, since it is perfect, so the incoming electron it can move freely if had it not been perfect. So that is why there is a decrease in resistivity of the material. These are the smaller properties of a superlattice.